Good morning, everyone, and welcome to the 3-minute thesis competition organized by the Graduate Student Government at Michigan Tech. The 3-minute thesis competition celebrates the exciting research conducted by graduate students here at MTU. Developed by the University of Queensland, 3MT cultivates students' academic, presentation, and research communication skills. The competition supports their capacity to effectively explain their research in 3 minutes in a language appropriate to a non-specialist audience. The real scope of the challenge can be really felt in 3MT's tagline. Quote, an 80,000-word PhD thesis would take 9 hours to present. Your time limit, 3 minutes. That makes it exciting. The presenters we have here today have taken on this challenge. The rules are simple. Each presenter gets 3 minutes to present their research with a single static PowerPoint slide. So the order of our presenters today is here. The participants here can have a look at their number before we call them up on stage. And our first presenter today is Zongda Liu from the Department of Civil, Environmental, and Geospatial Engineering. And their topic of presentation today is development of a new, durable, and energy-efficient pavement material. Please welcome Zongda Liu.
So there'll just be a quick 10-second countdown on the clock. No, you're good.
No, you're good. So
I'm
this
just-
is the time you can see when it's finished, and it will give you in the beginning a 10-minute countdown. So you're ready.
Okay.
Thank you.
And I will stop you right as time expires. So.
Okay, hello everyone. My name is Zhongda Liu from civil engineering. I'm a PhD student and new here. Today my topic is new durable and energy-efficient pavement development. From the first bridge in England to the Sea-Cross bridges today, we can see the bridge tech developed. But the steel bridge is better and better, but the pavement material on the steel bridge is not that good. We can see every pavement material nowadays usually use some asphalt pavement material. It's very weak and always bear in these effects. We very humor call it this floor effect, and it's like road breeze and slides and in the water effect. So by these things bear this effect, it's very weak. So what's our method? Our method is don't use asphalt material. We design a new polymer. Use the polyurethane to this thing, and we have two key issues. Because of time, I don't put them very specifically. We use this method and design a new material and make it have a balance, high temperature, low temperature, and water property. So after we design it, we can see nowadays the best pavement material on bridge deck usually use these two. It mixed by asphalt, but our polymer concrete, everything is maybe about around 10 times to them. Here's high temperature, low temperature, and water goes through. So after our material done, we have made it in China many places. This is a big steel bridge we use here, and we have many patents and some test reports. and my new
time.
industry standard here. Thank you so much.
Thank you.
Have a seat.
Thank you so much.
And we will invite the next speaker. So our next presenter is Shivayogi Aki, and his research topic is benchmarking model predictive control and reinforcement learning for legged robot locomotion. Please welcome Shivayogi Aki.
We can have a couple. We'll start in a couple.
Thank you.
Right.
Okay, hello everyone. Quadrupedal robots. I'm pretty sure everybody's seen four-legged robots on YouTube, and they've been very trending in the past few years because of their severe advantage over wheeled robots, because they can travel in places, uneven terrains that are harder for wheeled robots. So, have you ever wondered how a quadrupedal robot walks? So we've compared a few of the brains that we call controllers for quadrupedal robots. The past few years, the most trending robot controllers have been model predictive control, MPC, and reinforcement learning, RL. So what is model predictive control? Model predictive control is a optimization-based controller, and reinforcement learning is a trial and error based controller where the robot interacts with the environment and learns. So what we realized while comparing these two is to compare controllers, two brains, you need to standardize them, make sure they're on equal footing. That's what's being done in the first plot right there. And in perturbation, we compared three situations where the robot is walking without falling and stumbling, second while the robot is stumbling, and the third while the robot falls completely over. In the first situation, we realized that, okay, reinforcement learning is actually slightly better. But then in the second situation where the robot stumbles and it involves a recovery process, we realized that MPC does much better. There's a drastic improvement. But then In the third, where the robot ends up in a state of failure, which is the robot falls over on its back or the joints get completely interlocked. In situations like that, both the controllers unfortunately fail. They cannot recover. And the third most important task that we compare is generalization, which is the test of adaptability, especially for reinforcement learning, because it is trained within one environment and it needs to be compared. Okay, let's say I train it in a flat friction surface, and then I want to check if it works still on a slippery surface or an uneven surface. And we notice that the distance travel reduces, but it still is manages to walk. And at the end of the research, we realized that, okay, they have their own advantages and disadvantages. And this is something that needs to be combined and integrated in the future. And eventually we hope that, okay, our robot right there, it will be able to walk through the rocky surface and then maybe even swim and reach the lighthouse. Thank you.
Everyone is welcome to help themselves to coffee, lemonade, and pastries and muffins out there. So feel free in between presentations to help yourself and those out there.
So it's time to welcome our next participant. Our next participant is Satya Pili from the Department of Mechanical Engineering, Engineering Mechanics. And the topic of presentation is increasing efficiency for a hybrid model. Please welcome Satya Pili.
Hi everyone, my name is Satsai Kumar Pili and I'm from Mechanical Engineering, Engineering Mechanics Department and I'm a graduate student. So my research topic is about.
Hold on just a second. As soon as that hits 3, you can go.
Oh, there's a timer.
Here we can reset.
Hi everyone, I'm Satsai Kumar Pili and I'm from Mechanical Engineering Department and I'm a graduate student. My topic is about increasing the efficiency of a hybrid model. Before jumping into the efficiency, let's talk about what exactly is a hybrid model. Hybrid model is two different types of technologies are used in a hybrid model. One is 3D printing and the second one is material removal process. And in our research, we've been using milling process. So what exactly is a 3D printing? 3D printing technology is a rapid prototyping technique that we use to fabricate a product by printing it layer by layer from the bottom to the top in all XYZ directions. To understand what exactly is 3D printing, we'll take an example of how we prepare a cake. A cake is prepared by applying cream layer by layer from the bottom to the top. That's exactly how 3D printing works. Now, talking about milling. Milling is a material removal process. And to understand it well, let's bring back the example that we took to understand 3D printing. Now, what happens when we have excess cream on our cake? We'll just remove it with a knife. That's exactly what milling does. It removes the excess part that has been deposited on the surface of the product that has been just came from 3D printing. Now, the thing is, when exactly we have to do this milling process? Unlike cake, the material that we're using in our 3D printing is VAM, is steel. So it acts quite different when we are subjected it to higher temperature. Now, when exactly do we have to do this milling process is the biggest question. And to answer that question, we've been doing a lot of research and we have done a lot of test runs and found a beautiful relationship between temperature and height of the melt material. So we've taken 3 layers each from 20 degrees to 70 degrees temperature. For each temperature, we have seen a gradual increase in the height of the melt material. And after 70, it has been a straight line because we can't see difference between the height of the melt layers. Now, if we can actually find the height of the melt material based upon the temperature that we are giving as input, we can actually automate this process. Usually, after printing 3 layers, we have to measure the height of the melt material and then give the values to the end effector or the robot that is doing this milling process. Now, if we can just find the value of the height based upon the temperature that we are giving, we can automate this process by giving the values well before it is printed to a robot who is working on this milling process. So that when 3 layers are printed, it does this operation automatically, even if without an influence of an operator. So that we can actually save a lot of time. We can actually improve the overall efficiency of this hybrid model. And again, hybrid model is not a mission, but it is a combination of 2 technologies. One is 3D printing and the other one is milling process working together simultaneously for a single output. Thank you.
So moving on to our next participant. Our next participant is Tagore Rao Kosareddy from the Department of Computer Science. And the research topic he is presenting is dish robotics. Please welcome Tagore Rao.
This is not the slide. I have updated it.
Is it okay?
Right.
It's gonna give you a 10-second countdown time, right?
I'm gonna keep it simple. Many people have different objectives on doing research or PhD somewhat. But if I do some research, the main objective is to solve some problem in a society that is existing for a long period of time, and that will positively impact the people's life. In America, for 43% people of fight or doing dishes, and about in a year they fight over to 17 times. And I work in DHH, that is a dining hall. And I started working one day, I was like doing the dishes and it is boring, pretty much boring. So I started doing them in a matrix form, placed them in a matrix form. After I tried with the stack form, I started doing things differently and I found out, okay, we can do something with difference. There are there is a whole section for washing, and there are continuously 5 people continuously working to wash the dishes. And the numbers, let's talk about the numbers I would love that. So for chemicals, they use $1 per hour, and the time is 3 minutes per one dish. And the gallons water is 1 gallon they use on one dish, just one dish. I don't know how many dishes. There is a continuous repeated process, so I couldn't keep count. And let's talk about the money. Per hour, they spend $40 per hour for washing one dishes. And you take only that, there is only one DHH. This is the approximate information got from the chief manager of the DHH. We don't know about watts, we don't know about the MUB, and we don't know about the McNair. Take about the whole food industry that is in America, all the educational institution, how much wastage and how much chemicals there, don't know. So the motivation is obviously, as an engineer, I want to do these things differently. And yeah, if you take washing machine, it will wash clothes. It is an open loop system. It doesn't tell you how much good clothes you are. So I'm gonna give you degree of washing and degree of cleaning. We're gonna run some image segmentation with the transformers and get some scale on how much we can perform with the cleaning with these 2 factors and some irrational thinking. If these, how much these dirty are and how much force we have to do with the robotics. Basically, I'm going to give you a good dishwasher. You can ask me a question, why do you need a dishwasher? And I'm going to answer your question with you, like, even after so many centuries, why there is a need of hand washing? Why can't we eradicate? That's why I'm simply trying to do that with our research areas, computer vision, machine learning, artificial intelligence, and robotics. There are so many research papers we can create on this topic. And yeah, there is a lot of money we can make also. And maybe there will be people not fighting over about it, doing dishwashing in future. I would like to see that. Thank you.
Moving on to our next contestant. Please welcome Ravi Thakur from the Department of Applied Computing, and the topic of presentation is experimental learning opportunities in mechatronics to promote a diverse STEM workforce. Please welcome Ravi.
Ladies and gentlemen, and esteemed judges and fellow enthusiasts of scientific innovation. It is both honor and privilege to stand before you as a research assistant deeply invested in the transformative potential of mechatronics education. My name is Ravi Thakur, and I am driven by the belief that the I have been driven by the belief that the mechatronics education holds a lot of potential, and it should include diversity and workforce of the STEM. And our research project, Excellent Empowering Next Generation Mechatronics, has been guided by a set of goals where we want to promote diversity and inclusivity in STEM workforce. So our goal has been set by ambitious, set achievable goals by providing enhancing mechatronics learning and providing hands-on training to the under diversity and community college students. And none of this would have been possible without the collaborative efforts of Michigan Tech, community colleges, universities, and industry people. And our research approach focuses on meeting the academic knowledge with real world applications. And more importantly, our research work calls for the diversity in the STEM workforce through bridging the gap and fostering more inclusive work environment. And in conclusion, Excellent is not just an initiative; it is the movement towards the future where possibilities of mechatronics are endless and accessible to all. And that's it. Thank you.
There are refreshments outside, so please enjoy them while they're there. It's for everyone. Yeah. So moving on to the next presentation. Our next presentation is by Rivant Mehti from the Department of Mechanical Engineering, Engineering Mechanics. And their topic of presentation is uncertainty quantification for fracture of 3D printed materials. Please welcome Rivant.
I'll give you 10 seconds, start with the 3. Shows up.
Okay, so hello everyone, good morning. My name is Rivant and I'm a fourth year PhD candidate in meme. And I guess everyone might have heard of 3D printing. One of our friends was explaining it earlier. 3D printing is a revolutionary manufacturing technique. It has a tremendous amount of potential and a lot of research has been going on in the past 2 decades. The key advantages are the material properties can be fine-tuned to the requirement, but there are some difficulties with the end products. So let's say with a particular set of printing parameters, here as you see, the layer, the 3D printing process happens by layer build up. We can vary the raster angle, the temperature of the molten material which is coming out of the nozzle. There are many factors. Like there are, in my experience, for a simple 3D printer, there are 15 to 20 printing parameters which could affect the final structural durability. Now, my research focuses on understanding the variation, the effect of these parameters in the final response of the material. So let's say if you're trying to print a component which is used in electronics, let's say in a mobile phone. Now, there are certain requirements which let's say it has to withstand a force of 20 newtons. Now, these kinds of requirements are there, or there's a requirement of the such as 30 to 40 newtons. Now, the advantage of this kind of process is we can fine tune the material properties. That's what my research is. What we do is we initially to understand how the material behaves. We perform some experiments, and then we build a mathematical model to understand these experiments or to reproduce these experiments. But when we try to go into this Bayesian framework, which has been in the literature since the past 3 centuries, so it is a pretty powerful idea. So in the Bayesian framework, if you have some prior knowledge of these printing parameters, let's say if you want to change the printing angle as shown here, 0 to 90 degrees. Now you know that the printing angle can't exceed 90 degrees. So if you have this prior knowledge, and then let's say if you have your requirements such as my strength should be like 20 megapascals or 15 to 20 megapascals, I put in through this black box model or this uncertainty quantification model, which gives me these outputs are the requirements. Now, the final end result would be this posterior distribution. That's the thing, which is, let's say, for this strength values which I was talking, I'll get a final printing angle of 30 to 40 degrees. So it would give me this final printing parameters approximation. So we have some printing parameters which can be varied, and now we finally have an uncertainty measure of them. And we use surrogate models which can reduce the time scales to orders of magnitude.
And time.
Yes.
Okay. Our next presentation is by Ilyana Sempik from the Department of Biological Sciences. And the topic of presentation is investigating the mitochondrial function of miRNA 483 deficient pancreatic islets. I hope I said the last word right. Please welcome Ilyana.
I'll give you a 10-second countdown.
Hi, everyone. Imagine yourself in a sinking boat in the middle of the ocean. You are thinking about ways to stop the boat from sinking and ideally patch the hole that's causing you to sink. But the only way you can stop the boat from sinking is by throwing buckets of water off the boat. While this may decrease the water levels in the boat, it is not a fix for the hole, and ultimately you are still going to sink. This is similar to the current treatments available for type 2 diabetes, a disease affecting over 450 million people worldwide. Current treatments target the hormonal imbalance contributing to high blood sugar, but this is only a preventative measure, like throwing buckets of water off your sinking ship. In my research, I am hoping to gain a better understanding of the initial hole in the type 2 diabetes ship and identify the cellular processes at the root cause of the disease. It has already been identified that the initial hole in the type 2 diabetes ship is a process called dedifferentiation that causes impaired insulin release. This is a process in which mature cells travel backwards along their maturation process and become immature again. To investigate dedifferentiation, we have simulated this process in mouse models using small RNA molecules called microRNAs. These molecules regulate the production of proteins, a major factor in cell function. In mice, a specific microRNA called miR483 protects the maturity of the insulin-producing beta cells found in the pancreas. When this microRNA, miR483, is removed from these mice, dedifferentiation occurs, resulting in immature beta cells that produce less insulin. We seek to understand exactly what is happening in this dedifferentiation process that causes impaired insulin release in order to reverse this process or patch this hole. To do this, we must first look at what cellular processes could contribute to the impaired insulin release seen after dedifferentiation. Every cell needs energy, or ATP, to function within the body. The main processes that produce energy are glycolysis and mitochondrial respiration, and the combination of these allows the cell to perform vital day-to-day functions like the production of proteins. I've evaluated both of these processes to understand how they intertwine in dedifferentiated beta cells and gain insights on how dedifferentiation causes that loss in insulin production. In dedifferentiated beta cells, I have found both respiration and glycolysis produced little energy compared to functional beta cells. This shows a direct correlation between dedifferentiation and the overall loss of energy production within the cells and gets us one step closer to patching the hole that began diabetes. Thank you.
So moving towards the second last presentation of Heat One. The presentation is by Tucker Nielsen from the Department of Humanities, and the topic of presentation is deconstructing writing with Lego, a method to engage post-secondary STEM students in writing classrooms. Please welcome Tucker.
The 10-second countdown.
It takes more than strong math and science skills to be a great mechanical engineer in the 21st century. To meet the challenges ahead, mechanical engineers must be able to communicate clearly in a variety of modes to diverse audiences and across cultures. This quote comes from Michigan Tech's Mechanical Engineering Mechanics Technical Communications webpage, demonstrating the ongoing challenge of teaching communication/writing skills alongside technical skills. STEAM fields across campus and other institutions work to incorporate both of these, yet not all students grasp the connections due to their learning styles clashing with how the material is presented. As an addition to the ongoing solutions for interdisciplinary writing pedagogy, I present my study of incorporating Lego bricks into writing classrooms. Using communications theory, play philosophy, metonymy and metaphor, and role play, the study incorporates students of visual and tactile learning methods to improve their writing skills for their classes and their careers. Next semester, I will teach a modified section of UN 1015, or composition, with each core assignment consisting of one lesson with Lego bricks. These parts will be used in lesson activities, such as building solutions for prompts, acting out assignment sheets, communicating building steps to others, and translating research topics into interactive models. Each activity will have a written reflection asking students to consider their choices, think about the communication skills with the assignment, evaluate their end product's effectiveness to the problem, and consider alternative solutions/possible improvements. This interdisciplinary study intends to build up every student's confidence in their communication skills and provide the tools for their success in their chosen field. The study also encourages professionals outside of writing pedagogy to contribute and modify these methods as need be to suit their field's communicative demands, such as source documentation for computer science, reports for material science labs, qualitative results for social sciences, and equipment instructions for backstage technology. Studies such as this may improve how educators reapproach interdisciplinary communicative pedagogy, especially regarding student inclusivity. Thank you.
So it has been an exciting hour of grad students sharing their researches from all sorts of different departments. We are here at the last presenter of Heat 1 contestants. And this presentation is by Gustavo Bejar Lopez from the Department of Geological and Mining Engineering and Sciences. And the research topic is an interdisciplinary approach for the characterization of lahars on Volcan de Fuego, Guatemala. Please welcome Gustavo.
One second.
Okay, imagine it's the middle of the night and you hear a volcano roaring in the distance, but you don't worry about it much because you know the volcano is far and you feel relatively safe, so you go to bed. But hours later, you wake up to the ground shaking, and minutes after, your house is dragged away with you in it. This sounds like the plot for a terror movie, but it actually happened in Colombia in 1985. Here, lahars from the Nevado del Ruiz volcano destroyed the city of Armero and killed over 23,000 people. So what are these lahars and why are they so dangerous? Well, lahars are a type of volcanic hazard. Think of them as a mud flow. They occur when all this loose rock, ash, and debris sitting on the steep flanks of volcanoes mix with water from rainfall, from glacial melt, and that mixture, which resembles concrete, flows downhill at great speeds, and often without the intervention of a volcanic eruption. Like they do in Volcán de Fuego in Guatemala, where every month, tens of lahars occur at the peak of the local rainy season. And while lahars on Volcán de Fuego are not as big as in Armero, Colombia, they can still hit communities directly. For that reason, I'm using a set of sensors located around the volcano that allow me to better understand how these flows initiate and how they behave as they move across the landscape. Among these sensors, there are seismometers, which are like microphones for the ground. They record the ground vibrations generated by lahars as they move. These ground vibrations, or seismic waves, they're just like sound, but instead of traveling through air, they actually travel through rock. And just as with sound, they can be loud or quiet, and come in combinations of frequencies with high frequencies and low frequencies. Well, using machine learning methods, I have unraveled the hidden patterns in those combinations of frequencies and other rock sound parameters, allowing me to train models that automatically detect when those patterns are active, leading to real-time lahar detection alerts. And as of now, I'm also testing a system that delivers those alerts to your phone. This project also involves the use of rainfall data as a way to describe the water source for these flows, and in the future, generate computational models that simulate lahar behavior. Overall, these real-time lahar alerts and these improved computational lahar models will be a game changer for the people in the communities at more risk around Fuego, as they bring us closer to delivering better tools for hazard mitigation and potentially saving lives. Thank you.
So the presentations by the contestants for Heat 1 are finished here, and we will be continuing with Heat 2 contestants at 11:05. Meanwhile, you all are encouraged to enjoy the refreshments outside, and yeah, see you in a while. Thank you. That's it. Yeah.
Resources. And so I want to try and flip the conversation 180 degrees, because usually we think, what can viruses do to us? But I want us to think about what might we do to viruses living with humans, specifically SARS-CoV-2. So when they're in our cells using our resources, our enzymatic machinery, in a sense, they're at the mercy of our internal functionings.
And what is found is that when RNA viruses do enter human cells, they are modified by our epigenetic machinery. So we wanted to look at this and understand, is this good for the virus? Is this bad for the virus? And how we did this is we synthesized various RNA strands with different modifications that are found in our bodies in this room right now. And we annealed these 30-mer templates with the 20-mer primer there on the top, 1A. And we incubated these annealed RNA molecules with the SARS-CoV-2 replication complex, the very virus that's used to synthesize RNA for the viral genome for replication, proliferation, and reinfection of other individuals. So when we incubated these double-stranded RNA molecules, the SARS-CoV-2 replication complex elongated that missing segment up there of that 20-mer primer to the 30-mer primer. And so when it elongated there, we were able to see what the effects of the modification were on the SARS-CoV-2 replication complex. We analyzed that by gel analysis. You can see here as time goes on, the top band is the 30-mer elongated primer. So that 20-mer primer elongated to 30 nucleotides. And for the most part, we saw what we saw here in this gel, that intensity is slowly increasing as time increases, which makes sense, elongation increases. But one modification caused a severe problem for the virus, M1A. And M1A was the 1F RNA template there. And what we found in M1A is complete termination of elongation. And that is best seen in these gels here on the bottom right corner. So this lane right here on the left is M1A. On the right is pseudouridine modification, and you can see there's different lengths for both of those modifications. The M1A being shorter, showing us that it was terminated completely. And this causes huge problems for the virus. It cannot replicate with this modification. And this gives us an understanding of how we can use this information to develop natural antiviral drugs, but also to use it clinically to understand M1A expression in different individuals and how we might treat people differently. Thank you.
right,
Nice to meet you.
so as we get ready for our next presenter today is Kohina Ofori. Lead us up.
I'm setting time down, countdown. Go.
Good morning, panel members. My name is Governor Alfori, and I'm here to discuss mineral carbonation of mine tailings as a solution pivotal to the transition from fossil fuels to sustainable technologies. As we shift towards battery-powered systems, the demand for critical minerals increases, lithium, nickel, cobalt, and the rest. But we are at the crossroads where mining has to evolve to mitigate its own environmental footprint. As we enjoy our mobile phones and laptops, and as we embrace electric vehicles and renewable technologies, it is very important that critical minerals be delivered or be mined. And so does mining become very important. But yet, the challenge is that mining poses a lot of environmental challenges to us. And there is the aim to transform mining into zero impact mining. In my research, we use mine tailings from mining sites that produce critical minerals to react with carbon dioxide. This is because these mine tailings, which are silicate minerals, are very reactive with carbon dioxide and can react to form stable carbonate that can be stored over a long period of time. So what we do in a typical reaction is to take carbon dioxide from power plants or industries, take the waste from mining, and then we put into a reactor and then react with carbon dioxide to form stable carbonate that can be stored subaqueously, that can be used for construction of roads, and that can be applied in so many things. We also study catalytic chemistries to understand how we can speed up the rate of reaction, and also we use advanced mineral advanced mineral recovery processes like sulfidation and complexation reactions to recover traces of critical minerals that may have been lost in the waste of the mining. Our goal is to refine the carbonation process to make it energy efficient and also to make it economical. At the end of the day, we seek to obtain two goals: to create a closed loop system that can support the transition of energy, and also to create zero impact mining as a standard. By so doing, we ensure that the future, the very foundations of our battery-powered future is built on sustainable practices that is good for our environment and protects our planet. Thank you.
All right, and let's welcome our next presenter today, Cody Tufte.
Give you a 10-second countdown.
Hello, today I'd like to discuss with you guys corneal wound repair. Now, why is this important? Well, corneal scarring is one of the leading causes of blindness worldwide, and the procedure to correct this is cornea transplant surgery. Now, during this surgery, an incision is made on the side of the cornea where the surgeon will go in and perform the transplantation. However, with most surgeries, healing of that incision is very important. Now, traditional methods like sutures, as we can see in the bottom right, will cause a lot of inflammation and scarring from the immune system. Obviously, in the cornea, when we're trying to heal blindness, creating more opacity in the cornea is not ideal. Now, this inflammatory response is caused, and scar tissue, is caused by an overexpression of collagen from the surrounding cells caused by the infiltrating immune cells. Now, there's also commercial sealants out there that have tried to minimize this inflammatory effect by reducing the physical trauma happening from sutures by using a normal glue or to seal fibrinogen glue. Now, the problem with this is it doesn't allow cells to migrate into this. But why is this a problem? Well, as the body reacts to an implanted material, it detects the size of the material by immune cells coming to that place, and then will mount a proportional immune response to it. So what I propose is a tissue repairing glue that uses granular hydrogels to allow cells to migrate through this. Now, how does this work, you might ask? So granular hydrogel is made up of many packed together microscale water-based gels or hydrogels. Similar to a bin full of soccer balls, this allows cells to migrate through those interstitial spaces between all the microgels, allowing the immune cells coming to the wound site to infiltrate the scaffold without resistance. Now, additional to this, it allows cells to proliferate and grow throughout it as if they had produced a heavy collagen scaffold without having to eat through any other solid material such as the commercial sealant. And what this also allows us to do is it gives us a plug-and-play modularity as we can change the composition of the granular hydrogel with different microgels. So we can load those microgels with bioactive agents. Now, using this, we would like to reduce the inflammatory response by the body or immunomodulation. But what is immunomodulation? Immunomodulation is the engineered adjustment of the body's immune response to an implanted biomaterial. So what I propose is two bioactive components to inhibit or reduce this response. The first is exosomes, which is a naturally derived nanoparticle from stem cells. Now, these nanoparticles will reduce the inflammatory response by the immune system and then increase the pro-regenerative response to give us a quicker healing time and reduce the amount of scar tissue initially formed. Now, further, interleukin-10 will inhibit the collagen synthesis by those inflammatory cells. So as we decrease the inflammatory response, we also decrease the amount of scar tissue. The combination of these two in a granular hydrogel will allow a seamless healing after a surgery. Thank you.
All right, and our next presenter today is Henry Summers.
Coronary artery disease is the leading cause of morbidity and mortality in the United States and third leading cause worldwide as of 2023. The disease is classified by a buildup of plaque inside arteries that supply the heart with oxygenated blood. This plaque, which is made up of cholesterol deposits, narrows the artery and hinders adequate blood flow, often leading to cardiac arrest. Very small mesh tubes, called stents, are inserted into the diseased artery and expanded using a balloon catheter to compress the plaque and restore adequate blood flow. These stents are traditionally composed of metallic alloys that permanently remain in the body after implantation. However, there are clinical concerns with the long-term residency of an implanted stent in the human body, including mechanical failure of the device and adverse biological reactions which hinder the healing process. Motivated by the health risks with permanent stents, researchers have turned their attention to the development of temporary bioresorbable stents. Bioresorbable stents are composed of materials that are designed to provide temporary support to the artery while healing takes place and then be harmlessly broken down and excreted by the body. Some of the most promising candidate materials for bioresorbable stents are zinc-based alloys. This is because zinc naturally degrades in the human body at a rate which allows sufficient healing to occur before being completely broken down. Over the last decade, researchers have made significant improvements to the strength and ductility of alloys that could be used to construct stents through small additions of other biocompatible elements such as magnesium or copper to zinc. However, a major problem remains. No one has studied how long these zinc alloy stents can withstand the forces that are imposed on them by the body while they are also actively breaking down. As the patient's heart pumps blood through the artery, cyclical forces are imposed onto the stent as the artery contracts and expands. This type of loading, called fatigue, is like if you were to bend a paperclip back and forth until it eventually broke. In addition to the fatigue loading, stent failure by a mechanism known as creep poses a substantial threat to the efficacy of these devices. Creep is easily understood if you imagine a small weight suspended from one end of a wire. Eventually, the force of the weight will elongate the wire over a long period of time. The same kind of deformation occurs along the length of an implanted stent because of constant arterial pressures. In both fatigue and creep loading scenarios, the material eventually forms cracks which get larger and larger until the stent breaks. Because these stents are actively corroding as they're undergoing these forces, it increases the rate at which cracks form. My research will characterize how drastically a simulated body environment quickens the failure of zinc alloys by both fatigue and creep mechanisms. I will explore different manufacturing processes such as thermal treatment and hot extrusion and see how they can improve zinc alloys and make them more mechanically stable while also undergoing corrosion. Thank you.
All right, and now let's welcome our next participant today, Katrina Carlson.
Good morning. Questions remain as to why students who enter orientation take the produced spatial visualization test with rotations, pictured here, and fail it, have to take a remedial spatial visualization course, Engineering 1002, end up doing better in their first year STEM courses, such as chemistry, calculus, and computer science. One of the answers might be that students gain in their confidence or their self-efficacy in the skills that they know to be important to them as an engineering student and also to their future career as an engineer. Now, you might be thinking that self-esteem is the same as self-efficacy, but it's not. Self-efficacy is the confidence in affecting your future, in attaining your future goals. According to Albert Bandura, psychologist, self-efficacy is the product of past experiences, observation, persuasion, and emotion. Now you can see examples here of the LACI, the longitudinal assessment of engineering self-efficacy, such as I can complete any engineering degree at this institution. I expect to feel a part of the group on the job if I enter engineering, and I can complete any math requirement for most engineering majors. These are examples of statements that students rated on a Likert scale, and there are 31 items. And as you can see here, the Engineering 1002 students, the spatial visualization, ended up increasing their scores from the beginning of the semester to the end of the semester, as compared to 1102 students who are in their second semester, first year. Now, there was a relatively small sample size for 1002. And so my future research is going to look at two groups that are compared in size, so relatively similar sample sizes, and also both first year, first semester engineering students. Oh, geez, I apologize. So self-efficacy is important when it comes to students' ability to succeed in their academic subjects and also in their persistence to complete a major. The question remains, does the spatial visualization course increase students' engineering self-efficacy as well as their spatial skills? Thank you.
Right, and our next contestants today is Praise Aaron Mosley. Aaron Mosley. Praise. No? Okay. Turn them on to the next one. Yeah, you can check the whole. All right, never mind. We're going to be hearing from William Hansen.
That gets to 0. Yep. My research topic is predicting mine tailings carbonation reactions. So mine tailing carbonation, take a sample of mine tailings, react it with CO2 and the calcium oxide, magnesium oxide, iron oxide in that will form carbonated minerals. And this is done to sequester the atmospheric CO2. And there are a lot of factors that affect this, how much carbonated minerals that are formed out of this. The ones that I'm focused on are temperature, pressure, of the CO2, and also the reaction time. So to study these, Kobina and I do mine tailings carbonation reactions. And with that data, that then becomes the data used to model with machine learning the carbonation of different products. So for the models, we do gradient boost, which is more focused on splitting the data into groups and then calculating the average prediction of each group and correcting them to match the actual average. And then random forest, which is B, and that's a similar technique, except it's an average of each group instead of one iterative over the other. K nearest neighbor, that's focused on that the data points that are closest together will tend to have the most similar value. So the output of this model is based on how far away each of the different data points that we have is. And then neural networks, we just feed the different inputs into them. We optimize the weights. And also self-building neural network, where it's only a couple of weights optimized at a time, and this makes it easier to do with a small data set that we have. We only have 32 training data points, so it's important to be able to maximize what we can do with that. So for the results of this, the best model was the gradient boost, which is this one, and that shows the correlation between the predictions of this and the actual data. And as shown on the graphs, it's a very strong correlation, whereas with just a simple linear model, there's very little correlation between the actual carbonation and the predicted carbonation. But even beyond the gradient boost, every other model done, except for the large neural network, had a better predicted carbonation values and better correlation than just a simple linear model.
All right, and now we will be hearing next from Austin DePotty.
Have you ever looked under the hood of your car and wondered why so much equipment is dedicated just to cooling? New cars don't have just one radiator anymore, and all of those have associated material costs and decreases in fuel efficiency. It turns out that the lightweight metals that we use, such as aluminum, also have a major drawback, that when exposed to temperatures much above room temperature, they will lose the majority of their strength. The high-strength aluminum copper family of alloys is strengthened at room temperature by metastable precipitates that form a nice fine microstructure like shown on the left. When these are exposed to higher temperatures above about 250 degrees Celsius, those metastable precipitates want to go to their stable form and they grow coarser, larger, and you get an irreversible decrease in strength. My research focuses on creating a high temperature, high strength aluminum alloy that can be used for internal combustion engine applications or other high temperature applications. I start off with the current best commercial alloy and reduce the main strengthening element, copper, by about half. This is so that when I add in scandium, about 0.1% scandium, I don't form a detrimental compound. The end result of my alloy is that I trade off some room temperature strength for improved high temperature strength. My alloy is 20% better than the original alloy after 24 hours at 280 degrees. And I still need to do more testing, but it appears that my alloy is also tougher, easier to manufacture, and has better corrosion properties. If my alloy is adopted commercially, this would enable more uses in industries such as internal combustion engines with less cooling requirements, or in aerospace industries using lighter materials near the engines. Thank you.
All right, and our last presenter of Heat 2 is going to be Travis Wabernick.
Hi everyone, my name is Travis Wabernick. Today I'm going to be talking about prospecting water ice on the lunar surface. So to start, I'm going to start at the beginning. with the Artemis missions. So Artemis is NASA's new missions to go to Mars, to go to the moon and Mars and beyond, by setting up permanent infrastructure and permanent moon bases on the south pole of the moon. To do this, we need to do something called ISRU, or in situ resource utilization. It's hard to bring all that mass to the moon, so we need to use a lot of the resources that are there in the first place. In order to get moon bases that look somewhat like that, that's very expensive to do. One of these resources, however, that we want to get on the moon is water ice. Water ice is extremely useful for many, many reasons. It can be used for rocket fuel, it can be used for life support systems, and it's just a very valuable resource in general. However, it's kind of hard to find. The lunar south pole is of particular interest as it gets very, very cold and acts as a cold trap. So there's regions on the south of the moon called permanently shaded regions. These are craters that never see the light of sun. So they reach temperatures below 110 Kelvin, which allows for stable water ice. So in order to investigate this, we've been looking at using prospecting rovers called a cone penetrometer. So the percussive cone penetrometer uses a heater to heat up this water ice in some of our experiments and simulations. You see these temperature profile curves. These temperature profile curves we can measure against the baseline of dry regolith and icy regolith. And depending on how much heat is absorbed through the late heat sublimation, we can determine how much water is in there. In theory, it's a bit harder than that in practice, seeing as you haven't been to the moon in about 40 years. So we have to do a lot of preliminary studies to understand both our testing equipment and how we're actually going to do this. So one of the things that I've been working on is understanding how lunar regolith simulant, which is basically our best simulation of moon dust on Earth, works when you have water ice in it, how it sublimates in a vacuum. So we've been doing thermal vacuum testing of icy regolith at temperatures about -60°C, and somewhat vacuum pressures, and simulating these results. So one of the ways that we've been able to simulate these, and the best way we've found so far in order to figure out how much water ice is there, is by looking at the derivative plots of the temperature curve. So as you can see here, this is our temperature curve, and you can see there's slight bumps and changes in these derivatives that allow us to kind of estimate how much water ice is there. So in conclusion, this is still a work in progress, but we've learned a lot through this process and kind of determining where our knowledge gaps are in this field. Finding water ice on the moon is not really a thing we've done before, so there's a lot to learn. So future modeling is going to investigate kind of different forms of water ice and different ways of testing and kind of trying some assumptions against themselves. So, thank you.
All right, and now I'll let the judges finish up. We have about a 15-minute break, and we will be back in here at 12:01.
Eric's on the other side. Are you okay with that?
I'd like to look at the dog, that's all.
No, Eric from your office, right? Yeah. On Zoom.
Oh.
Eric's on Zoom. Right. Happens to be really quick.
Oh, there you go.
We have magic.
I think the application wasn't responded.
But it's. Was that? Yes, that's. Right. Okay.
All right, everyone, welcome back to Heat 3. So I will welcome everyone once again. The 3-minute thesis competition, it celebrates the exciting research that's conducted by our graduate students here at Tech. So it was developed by the University of Queensland, 3MT. It cultivates students' academic presentation and research communication skills. This competition, it supports their capacity to effectively explain their research in 3 minutes in a language that's appropriate for a non-specialist audience. The real scope of this challenge can be really felt in 3MT's tagline. An 80,000-word PhD thesis would take 9 hours to present. Your time limit is 3 minutes. The presenters here today have taken on this challenge. The rules are simple. Each presenter gets 3 minutes to present their research with a single static PowerPoint slide. So our first presenter today is Kendall Belopavlovich from Humanities.
Okay. We have to work with vocal cords here.
There you go, you get.
Talk's going, so. All right, good afternoon, everyone. My name is Kendall Belopavlovich, and I'm honored to be sharing my work with you today on the homelands of the Ojibwa people ceded by the Treaty of 1842. I want to share with you an overlooked story, one that I'm calling The Wild West in the East, Cowboys, Indians, Spaceship, and Samurai. It's not that the story isn't important, but it's been historically overlooked because, as a global media audience, we are just starting to come to terms with it. This issue is the destructive legacy of colonization practices present in media stereotypes of Indigenous people. These stereotypes perpetuate harmful misconceptions, which in turn directly contribute to how Indigenous people are treated socially, economically, and politically. By the end of this presentation, you'll know how to spot one of these stereotypical images, called the Hollywood Indian, and ask critical questions about their appearance in the media you consume. As a Japanese media fan and researcher, I consume a lot of manga and anime, which are Japanese forms of comics and cartoons, like what's shown on the slides behind me. In these media, I see characters like the one in red print behind me from Sarutobi Sasuke, a Hollywood Indian chief complete with war paint, headdress, and magical talisman. Visually, this character is constructed as a savage, historical figure. These visual markers, the costume, facial configuration, and historical positioning are indicative of the Hollywood Indian stereotype. And I ask, what is a Hollywood Indian doing in the desert with samurai? And why did Japanese artists want to draw them into their stories? They've been a fixture of Japanese media since about 1949, when artists like Osamu Tezuka of Astro Boy fame began to copy what they were seeing and loving in American Hollywood films and 10-cent comic books. His work is in the black print behind me. Instead of simply copy-pasting American Westerns, though, Japanese artists have made the Wild West their own with the help of deep space frontiers, samurai, and spaceships. Though they still use Hollywood Indians and cowboys as a symbolic shorthand of the Western genre. In my work, I analyze stereotypical representations of Indigenous people, like these Hollywood Indians, in order to call attention to social systems like media industries, which benefit from and perpetuate colonial agendas. I hope that you're now able to recognize the Hollywood Indian stereotype and to critically question where it comes from and what it's doing in your media too. More importantly, I hope you can ask who benefits from this stereotype use. Thank you.
Right, and our next presenter today is going to be Cuthbert Agba.
All right, it's going to be a 10-second count.
A very good afternoon to all of us. Let me introduce you to Sema, a friend from my childhood. Sema is a high school dropout. Sema has 3 children. To support his family, Sema has embarks on a challenging task every day. He has to collect plastic bottles from roadsides and scavenging them through landfills to collect the discarded items. He then takes them to recycling centers where he earns a meager income. This may seem like an isolated story. However, it is a reality for most people living around the world, especially in developing countries. Plastic waste, and it is an unfortunate situation that plastic waste is flooding all over the world, and it is a problem that causes clogging and affects the ecosystem as a whole. I my research, this leads to my research, where I look forward to creating an environmentally conscious solution to disposing and managing plastic waste. Basically, I'm using plastic waste in the production of roofing tiles. The major contributor to this growing crisis is PET, plastic waste. And in this solution, I look forward to helping people like SEMA find more dignity in the job they do, in the noble job that they do. And as well, this research opens up doors for more research and innovation in the space of managing plastic as a waste. Thank you.
I love that. Everything.
Right. And our next presenter today is going to be Yogendra Kanchapu from Applied Computing.
Hello all, a very good afternoon. So I hope we all have played with puzzles when we were kids. If we join those puzzles, we can see a beautiful picture on top of it. So now just assume that I gave you a complex piece because we all are grown-ups. So this complex piece of puzzle, imagine that it is a drug molecule or a drug. So now if you combine all these pieces together, you can see a beautiful picture. That is what you can see over there. So this is what I call it as polypharmacy. So here, this is like a sort of a treatment where all these pieces are together. So by that, we can understand how it is used to treat a patient. Now, this gets a little bit tricky when these two pieces are joining together, sometimes it forms a distorted picture. So this is the problem of the polypharmacy. And so what I'm trying to do is I'm trying to create a AI advanced solution. So I came up with this model, and now imagine you are walking through a party where each drug is a guest and they are interacting with each other and they are having some sort of mingling and sort of interactions. And there are also a couple of others which are not properly interacting. Now, this graphical neural network is the master party planner, which is in the middle. Through the lens of that, we can clearly understand the proper interactions and the blueprint. So that is how we'll be able to know what is the good interaction and what is not the good interaction. So that is about my model, and this is how I wish to build a safety and efficacious model so that this helps the patients to have a high quality of life and also reduced drug-drug interactions and also the side effects. So being a pharmacist, I just had the knowledge in the drugs, and now I'm learning all this graphical neural networks, and I got up with this idea. So thank you for hearing me out.
Alrighty, and our next presenter today is Vaishnavi Balambi from Electrical and Computer Engineering.
Okay.
As an autonomous vehicle algorithm developer over the last 4 years and analyzing over 20,000 kilometers of data recorded by radar, LiDAR, and camera, I've seen some of the funniest and the strangest things that have been recorded. Like this one time when a buffalo was classified as two-legged two human beings. And another time when very recently I was collecting data on a semi-truck with 10 of these sensors. We ended up crashing into a lamppost in downtown Detroit because this lamppost was out of the field of view of these sensors. What I'm trying to say is that these isolated autonomous systems are not enough to make the vehicle completely autonomous or independent. There is a requirement of shifting this isolated autonomous systems to more coordinated systems. And this is where I draw my motivation for my thesis. I make this a reinforcement learning problem. In that, I establish roadside units or infrastructures where vehicles can interact over vehicle to infrastructure communication. And the vehicles send their information such as their speed, the positioning, what is their fuel level over secure communication channels to the infrastructure. Within the infrastructure, the control system or the control algorithm evaluates the space and the time that these vehicles have to move around or to maneuver freely without colliding into each other or the road infrastructure. Now, the reward or the feedback that is given from the infrastructure is the speed that these vehicles have to operate. Now, this speed is given in such a way that the average speed of all the vehicles in a given vicinity of these infrastructures is maintained to the maximum below the allowable speed. Like for example, here I have evaluated for 10 vehicles in a stretch of 5 kilometers urban road infrastructure, which allows around 15 kilometers per hour of speed. I have been able to achieve a maximum of 9.81 kilometers per hour as an average speed of those 10 vehicles without colliding into each other. Now, how this serves my motivation? We are here trying to make a more connected and a coordinated system, which serves for the functions, the autonomous functions, such as collision avoidance and traffic mobility control, which ultimately helps in fuel efficiency, in better traffic rule management, without having to depend entirely on the isolated systems or the high processing computing sensors. And that's my thesis. Thank you.
Could you go back to the previous slide, just like this? Thank you.
Okay, and for our next presenter today, we're going to hear from Rixie Fazalova. Never mind. We'll be hearing from Chuck Harris.
We'll have a 10-second countdown and then you can start.
Awesome. Hi, I'm Chuck Harry. Thank you for joining me today. I'll be talking about our development of a low mass lunar compactor. This is part of a NASA grant, the Lunar Surface Technology Research Grant. Thanks for the funding there. Anyway, as you may or may not be aware, NASA is continuing with efforts to go back to the moon. By 2026 was the original metric, but the plan is to go and to stay on the moon. So in order to accomplish these goals, we need to have infrastructure that's built. We're looking at building lunar bases, having power transfer, many different elements in the lunar environment will require infrastructure as a foundation for building these larger structures. So we have to call on our knowledge of terrestrial site preparation, and in particular, my project is focused on lunar compaction. A lot of challenges that exist in the lunar environment are fundamentally changing what we have to do in order to produce technology that works. Much smaller things have to be made in order to fly. And in general, a sixth gravity means that any mass that you send to the moon has less of an actual force to actually work on the moon. So the design concept that we're working with now is using individual pin vibrated systems that will be pressed into the lunar regolith and vibrated. This provides an energy that allows individual particles to rearrange themselves into a more compact state. We also have a surface pressure plate that kind of provides a bounding box to the to the regolith, which then makes sure that it doesn't flop up the regolith, which is actually something that you often see if you're just vibrating a body. Like if you've ever seen like sand vibrated systems that kind of liquefy. So we're trying to avoid that and actually recompact it. We also have each pin designed to be independent such that if an obstacle is seen during the compaction, you're still compacting most of the area despite hitting an obstacle or a locally compacted zone. So moving through our actual results, we've built a test setup using a singular pin and investigated a series of different frequencies in the range that is often used terrestrially. And we've seen a rough indication that the higher frequencies are more ideal. Our results so far, we've achieved 86% relative compaction. Our requirements from our grants are asking for 90% compaction, which is very difficult to do even terrestrially. But an 86% relative compaction is still meaningful, as many terrestrial applications are in the range of 70 to 90. So it's useful to be in any sort of increased compaction, but we're still looking to do some further optimization in order to achieve that 90%, which we have a number of metrics that we'll be looking at to continue this project. But that summarizes the project, and we're hoping that this technology can also have impact in terrestrially, as smaller and more effective devices tend to be effective terrestrially as well. Thank you.
All right. For our next presenter today, we have Abhishek Subramanian.
All right, you'll have a 10-second countdown.
Well, high-speed communication in the range of gigabytes per second is a necessity to realize autonomous vehicles between vehicles and infrastructure. Waves or millimeter waves is an ideal candidate here, which can give us such high speeds and their bands being unused by any other applications. Although waves are useful, they come with a serious problem, that is attenuation that they cause when they are obstructed by obstacles, because waves, millimeter waves, the wavelength is bigger. Now, to tackle this problem, rather than having a single antenna in the receiver and transmitter, how waves are designed is having multiple antenna elements on the receiver and transmitter. The process of selecting the best antenna between the receiver and transmitter is called beamforming. Now, typically beamforming takes around it takes around 150 to 200 milliseconds when we have 60 elements or 3,600 different combinations. When we talk about vehicular communication, this is a very large undesirable number, or we could say the latency is pretty high. And there is a need to reduce this latency. Leveraging the use of LiDAR camera or GPS or sensors such as that, which are already present on the vehicle, can be used to predict the empty spaces and ray tracing paths. I came up with this design of a fusion-based deep learning model where GPS and LiDAR are used as inputs, and it predicts the top K beamforming pair, where K is a subset of the total number of pairs, that is 3,600. So I was able to generate results where I was able to get an accuracy of 90% with just 32 beamforming pairs at a time of just 30 milliseconds, reducing the time from 150 millisecond to 30 millisecond. Moving forward, the data set that is already available, there is a hard bound on the data set, given the cost of generating or producing it. A federated learning paradigm can be used and is being proposed where the vehicles that are training, are using the model, the deep learning model, will also train on the go, so that unseen circumstances from previously can be also be trained. Thus is my research and the motivation of my research to use deep learning models in the physical layer of communication to improve them for the future. Thank you.
All right, so that concludes 3-minute thesis, our first round of that. I'd like to give a round of applause to our lovely judges. Thank you for volunteering. We have a gift waiting for you outside whenever you're finished up. And so we will see you again this evening for the second round.